Building a Bridge Out of Spaghetti by Josh, Shannon, Thomas, and Ethan. The task. This video covers the process of designing, building, and testing a spaghetti bridge with the goal of creating the lightest bridge capable of bearing the heaviest load. It was a collaborative effort over several weeks, entailing research, experimentation, and final design selection. The project offers insights into the world of engineering and underscores the significance of modern engineering and architecture in creating safe and efficient bridges globally. The design. The selected bridge design is a truss type, chosen for its recognized structural strength and load distribution characteristics, aligning with our project's objective to support the heaviest loads. Additionally, the truss design offers creative flexibility, allowing for a unique and personalized bridge construction, which appealed to our group. The chosen bridge design resulted from preliminary spaghetti strength trials. These trials provided insights into the bridge's potential load-bearing capacity by identifying the strongest number of spaghetti clumps. These will be talked more in depth later in the video. The design continued. The design and construction of the spaghetti bridges were undertaken as a group collaboratively. The group met several times to discuss and design a range of truss-style bridges. The bridges were made from both regular spaghetti and gluten-free. The drawings of the bridge designs were used to copy and construct the bridges. When designing the drawings, consideration needed to take place regarding the load-bearing members, and if there were enough members, as the load of the bridge would be transferred through those points. The math and physics. The diagram above displays the forces being exerted on each member of the spaghetti bridge. The red-pink members are the members under compression, and the darker the member, the greater the compression force. Similarly, the blue members are the members under tension, and the darker the member, the greater the tension force being exerted on the member. Resources. We used Sanremo's gluten-free pasta, normal pasta, and Selle's Super-Glue to produce our bridge. Selle Super-Glue was the only type of glue we were allowed to use. No other glue was permitted. This glue proved a challenge. It was very messy and sticky. This meant that we needed to put newspaper down to prevent damage to furniture and other items, as the glue was difficult to get off. A few times during construction, group members got glue on their hands, which slowed down the construction process, as they had to try and wash the glue off their hands. The initial testing. This is us testing the structural integrity of two spaghetti noodles. We tested gluten-free spaghetti and normal spaghetti, just to see if there was a structural difference between them. First test conducted was finding out the strengths and weaknesses of both sorts of spaghetti. It was found that the gluten-free spaghetti was strongest in tension, while the normal spaghetti was strongest in compression. From conducting this first test, it was concluded that for each member of the bridge, strands of both gluten-free and normal spaghetti would be combined to hopefully provide the maximum strength possible. The construction. In these photos, we are using our initial testing results and gluing our spaghetti strands together in bundles of 10 and slowly assembling the bridge. The final result. The final bridge managed to hold a total of 6.5 kilograms and weighed a total of 157 grams, meeting the necessary requirements. From the final test, the bridge demonstrated its weaknesses, allowing for the group to identify points of weakness that can be adjusted and kept in mind for future products. The bridge failed at point where the plate was attached, as the force wasn't being evenly spread across the bridge and was slightly off to one side of the bridge. A solution that was identified was the use of more spaghetti, as there was still plenty of weight to work with. More spaghetti could have been added to each of the members, providing a greater amount of structural support. Another alteration that could have taken place was a change in the shape of the bridge. While the shape of the truss bridge was effective when researched, it would be good to try different shapes to see which performs the best and conduct numerous tests prior to the final testing to allow for changes to be made to ensure the most structurally sound bridge. Because of the adhesive utilized, where applied, it caused the spaghetti to be brittle and reduced its structural integrity, creating weak points throughout the bridge and not allowing as much tension and compression as desired to be passed down through each of the members. Next time, different glue can be applied to reduce the chance of a weak point being created in the bridge, minimizing the total weight the bridge can support.